I just noticed that that lighter is in the vent to the laptop, and the laptop's fan is running, and it's heated it up, and I noticed it's bubbles coming up from the fuel valve. It seems like it's refillable. I don't think I'm going to catch it doing it. Well, now the laptop's not running the fan anymore because it's not playing the video. So. I was listening to Brian Loff talking about the cheap yellow displays. I'm thinking about my VGA project for Picos. But that was just a distraction. What I was looking at before was this post about using EPROMs and EEPROMs as programmable logic. And somebody's written a nice little Lisp example. It's that so you can write logical expressions on input pins and have them appear on these are the address pins, and these are the data pins that these expressions are evaluated on. And he gives some examples, some stuff, which EPROMs, and some thoughts. That's a nice little project, and but the reason I got there was I was looking at Alexei Radul's PhD thesis that he did with Sussman. That won't give you the URL. The URL is on this blog post I did about Sudoku. The URL for the thesis is that. And Kevin Cameron, this guy who worked on the transputer at Inmos, and he now lives in the States, and he's been thinking about computation on a very large scale, very distributed. He's talking about globally distributed, I mean literally worldwide, I think. But this idea of propagation networks. The reason I was thinking about that was I was thinking about linear algebra and vector calculus. And this idea that I have that's too vague to even put into words, it was to do with, basically, if you think about what a computer's doing, the display on this board, on this screen, is a series of pixels with integer values. And it's, if I can hold down the control key and hold the camera at the same time, it's full of floating point. These are splines that are being plotted. And as we scroll the screen, it's not smooth scrolling, but if it were, you would imagine those splines moving through space. No way is that. That's the smallest step I can do. But all of that floating point math that's going into plotting the characters using splines, in the end boils down to completely discrete integer processor operations. Or it could. I mean, this machine happens to have a floating point processor and it's probably being used to calculate the boundaries of those characters. But in principle, that could be being done with some kind of floating point library, as it would be in the Pico, because that doesn't have a floating point processor. It has a bunch of software that the CPU assembly somehow manages to, I don't know quite how that works, but they've got a little hack that they can do to, you can put floating point into software and still use floating point assembler, and it generates interrupts or something to do it. So if I connect that Pico to that display, it's doing entirely integer operations. And the question is, well, we know that that isn't the most efficient way to do it. If you're calculating a moving image of a spline curve, like the one that you see at the beginning of Freya Holmer's Continuity of Splines video, she kind of takes the splines, she decomposes them, plays that backwards, so that these splines come flying in from outer space and rearrange themselves into the word spline, and then she kind of zooms into the dot on the eye. If you imagine coding all of that, at no point, if you're only coding to the resolution of the display in terms of color and pitch, dot pitch, there's no necessity to compute anything beyond the kind of precision that can represent the spline curves that are the text. And the question is there a way, using this idea of global computation and local cells, and perhaps not interpreting that too concretely. Because if you look at the curve, is there an example on that screen in front of me? Yeah, I think there's a lot. All of the verticals on wonderful. The vertical of the D and the F and the L and the R are very probably, they're absolutely vertical, and the boundaries are straight lines. So in a sense, there's a piece of computation that could be distributed across all of those. The same process that computes those pixels could be computing them in all those places. Is there a way of arranging, taking some kind of high-level specification of a moving image in terms of splines and differential equations, and boiling it down to something like a cellular automaton, but with non-local connections to express the distributed nature of the abstract computations? If there was, then that would be a good thing to know how to do. You could compile a series of images into a matrix of propagators, in some sense, that propagate information from one point in space-time to another. And you could code that into some kind of logic. And the kind of logic that I was thinking about was the kind of logic that you can build if you have instead of an EEPROM, switching bus circuits on a serial bus. You imagine a very high-speed serial bus that is communicating bit streams, and the bit streams can represent operations, so that you can take 3 bit streams and use 2 of them as operands and 1 as an operator, and compute a part of a logical expression on that stream. If you built, instead of just an EEPROM with fixed logic, if that process was able to fold back on itself, use some kind of dual-ported RAM, the processes could program that bus according to their own output. That's the kind of level of computation that I'm talking about, physically realizing. And if I can there's some way to connect that computational model with the idea of cells, values being computed. That, if you think about the way that a character generator for a VGA display works when you haven't got enough memory to bitmap the display in RAM, what happens is you've got a block of memory which contains the pixels for each glyph, and then you have a representation of the text on the screen in terms of indices into the glyph table. And the process of generating scan lines, or generating the bit stream for the red, green, and blue wires that come out here, that process runs on you can run it on a Pi Pico. It knows the index along the scan line, and it knows therefore which glyph it should be scanning. It knows how far down the glyph it is. Each glyph is, say, 16 in the VGA, old IBM VGA font. It's 8 by 16 bits, pixels for each character. So it knows how far down the glyph it is, because that's just the modulo 16 of the scan line. It knows how far across, because that's the modulo 8 of the vertical position of the horizontal index. And it just does a lookup. So that process can write an entire scan line out and feed it to a PIO process, which just takes a bit at a time and outputs it on those 3 channels. And you can wire the display logic in to include the horizontal and vertical sync pins as well. So you've got a process which there's a bit of code that every place that, say, the letter A appears on your VGA display, there is a similar process that is running to generate the successive pixels, and it's scanning a line is then a question of saying, which process is it? We're here on this line. Now, which processes determine the color of the pixel at this point? And that's how sprites and things work. Or, for example, a mouse cursor. A mouse cursor is a separate process that runs on top of that scanning, character scanning process. And it takes, at any point, it can say, are we in the area where the mouse cursor sprite is at this point in time? If so, are we in the mask area of the mouse cursor sprite? If not, we show the underlying pixel. If we are, we look up the mouse cursor color for that point. So the mouse cursor comes as a color bitmap and a mask showing which parts are transparent. So that's incorporated into the scanline generator process. And what I'm talking about is a complete generalization of that, so that you've got little fragments of machine code which do these calculations almost as if they are BDDs or something. Now I'm thinking in terms of a von Neumann machine, but that's not what, that gives you some kind of aspect onto the computation. But what I want to do is not do it with a von Neumann machine. I want to do it with programmable bus logic on high-speed devices which are just made of FPGAs with very high-speed serial communications links. So what you would have to do is you would have to have the compiler for this thing is everything, because there's no way humanly you can handle that degree of complexity. So the compiler has to take a high-level expressions of moving images, and they can be in terms of input devices as well. So it can be in terms of a display position, a viewport, and projection. You would encode the entire 3D graphics pipeline into this spider's web of, or it's a kind of spider city of, you imagine 10 billion spiders like you get in forests in Africa, building a huge colony web. It's that kind of process. So you can see I'm a bit at sea with this, but I have an idea that in the end you can compute that certain values, which are things which would in arithmetic terms would be kind of averages, you can compute discretely by taking contradictory determinations of a value at a certain point, and letting the contradictions fight it out at that point in that cell, so that your cells, in Alexei Radul's sense, where a cell is information about a value, your cells are accepting possibly contradictory elements from other places, and by cycling through them in some sense, they can do an averaging process and produce the value. Now the question is, how do we design those? How do we design a system which computes that averaging process for each cell, so that it all starts to look a bit neural. And maybe that's an interesting place to use some of these neural computation ideas. Oh, it just bubbled. It's not going to bubble again for another half an hour. Never mind. That's a good ramble on that. That's the state of my mind right now. That's not particularly good. It's not going to get me a job.